How did a thriving tropical ocean disappear, only to be crushed and lifted 5 miles into the thin, frozen air of the Himalayas? Somewhere beneath the snow of Mount Everest lies the answer. A ghost story written in stone that changed the climate of our entire planet forever. At 29,032 feet, where the air is too thin to sustain human life, climbers tread on gray limestone embedded with the coiled shells of ammonites and the stony skeletons of corals. Creatures that once lived in the warm, shallow waters of a sea that simply ceased to exist. This is not an isolated anomaly. It is a fundamental geological paradox. The summit of the world's tallest peak is composed of the very seabed that once separated the Indian subcontinent from the vast expanse of Asia. How can the floor of an ocean be hoisted into the clouds? And what does this transition mean for the shifting atmospheric rhythms we experience today? The answer lies in a violent, multi-million-year collision, a mechanical grinding of plates that is not a finished monument, but an ongoing catastrophe that rerouted the wind and drew down the world's temperature. To understand how a seafloor became a summit, we have to look back to a time before the crash began, when the world was organized in a way we would barely recognize. Before this cataclysmic union, the world was ordered differently. To see how these peaks became the architects of our modern climate, we must follow a trail of evidence stretching back to a time when India was not a part of Asia at all. For millions of years, it drifted as a solitary island continent, fueled by a tectonic engine that pushed it north across 6,400 kilometers of open sea. It was a sprint in geological terms, with the landmass racing at up to 16 centimeters every year. This rapid transit across the Tethys Ocean hides a critical transformation. How that northward momentum shifted from a kinetic event into a global climate control system. We are left with a fundamental, unsettling question. How did a landscape so far beneath our notice become the very machine that regulates the seasons we live by today? And why is the collision of two land masses considered a turning point for the evolution of life on Earth? To answer this, we must return to the quiet world that existed before the first rock buckled. Back to the Triassic, 225 million years ago. Back then, Earth wore a different face. India sat locked deep within the southern supercontinent of Gondwana, anchored against the coasts of Africa, Madagascar, Antarctica, and Australia. It was not a traveler, but a prisoner of a massive, unified landmass. Along its northern border, the Tethys Ocean held the horizon, a warm, stable, and sprawling body of water where tropical reefs thrived in the sunlit shallows. Marine life flourished in these quiet waters, leaving behind the skeletal records of coral and ammonites that would, in time, be trapped within the rising rock. Yet, this arrangement was inherently unstable. Deep beneath the crust, the heat of the planet's interior was already shifting, building the forces that would eventually tear the supercontinent apart. The stability of the Triassic period masked a gathering tension. The tectonic plates were already locked into a configuration that could not hold. A change was imminent, a shift in the engine of the world that would soon sever India from its southern anchor and set the continent on a collision course with the north. What exact process would finally shatter the bond of Gondwana and launch India on its long, solitary drift across the abyss? The answer lies in a rift that began 200 million years ago. As the supercontinent Pangaea fractured, massive plumes of heat rose from the mantle, tearing the crust apart. India was wrenched away from the coast of Africa and Madagascar, stripped of its southern neighbors, and left as an isolated island continent. By 120 million years ago, it was adrift, a solitary landmass floating in the vast expanse of the Tethys. It was not merely drifting. It was caught in the grip of a tectonic conveyor belt. A slab of oceanic floor, far to the north, had begun to sink into the mantle, pulling the Indian plate along with it like a tethered vessel dragged toward a drain. The entire subcontinent was now locked into this trajectory, inexorably pulled toward the Eurasian margin. But how could a single tectonic plate sustain such a prolonged, high-speed transit across an entire ocean? And what unseen forces would eventually dictate the speed of that final, violent arrival? That transit was fueled by a tectonic engine hidden far beneath the waves. As the Tethys floor slid into the Earth's mantle, it acted like a colossal anchor, pulling the Indian plate northward with a force that defied conventional speeds. At its peak, India surged at nearly 16 centimeters per year, a pace faster than fingernails grow, a relentless, plate-sized sprint that outstripped almost anything else in the geological record. When Alfred Wegener first proposed that continents were not fixed but wandered the globe, he was met with ridicule. He lacked the mechanism to explain how a massive landmass could plow through the ocean floor. We now know that India didn't force its way through the sea. It was carried, riding the mantle's own deep-seated conveyor, with the sinking oceanic slab acting as the engine. Yet, this high-speed sprint toward Eurasia could not continue indefinitely. The sheer momentum of the plate was about to encounter an immovable resistance, a continental speed bump that would force the entire planet to shift its pace. But before the final, cataclysmic impact began, the stage was set by the global climate of the Eocene, where the greenhouse conditions of a hothouse world would soon be forced to confront a massive, rising obstruction. Across the Eocene, the planet breathed in heavy, humid heat. This was the epoch of the greenhouse peak, where palm forests and dense, broad-leaved angiosperms pushed toward the poles, finding a sanctuary even within the Arctic Circle. Crocodile relatives hunted in swamps that knew no frost, and the world was a single, lush hothouse Eden. Global temperatures climbed to among the highest of the entire Cenozoic, with a carbon-rich atmosphere sustaining a world that knew no permanent ice. Yet, this verdant stability hid the gathering weight of the approaching collision. Beneath this canopy, the continental drift continued, the oceanic slab of the Tethys silently sliding into the mantle to make way for the impending impact. The environment was uniform, rich, and deeply interconnected, yet the architecture of the globe was already being forced toward a radical fracture. As these vast tropical forests thrived, the first tectonic tremors of the coming upheaval waited at the edge of the horizon. If this warmth was the baseline of the world, what happens to such a fragile greenhouse paradise once the mountains begin to tear it apart? The answer arrived as a sudden, jarring halt. 50 million years ago, the relentless sprint of the Indian plate hit a wall. For eons, India carried its mass across the deep, silent floor of the Tethys, but here it met the rigid, thickened margin of the Eurasian continent. The momentum did not merely vanish. It translated into a violent tectonic speed bump. Velocity dropped sharply from 16 centimeters a year to just 4 or 6. This was the moment the two worlds jammed. Continental crust is fundamentally different from the heavy, thin, basaltic rock of the ocean floor. It is too light, too buoyant to be swallowed into the mantle. India could not slide beneath Asia, and Asia refused to yield. Trapped between the irresistible force of northward drive and the immovable barrier of the northern continent, the Earth's surface began to behave like a crushed car hood. The crust could not sink, so it had to rise. It buckled, it thickened, and it began to force the seabed out of the depths. As this wreckage began to lift, the deep-sea foundation of the Tethys was still caught in the middle of this catastrophic architecture, destined to be crushed out of existence entirely. As the Indian plate drove relentlessly into Eurasia, the Tethys did not simply vanish. Its oceanic crust was forced down, consumed into the mantle in a subduction zone, but the seafloor itself was a different story. The massive accumulation of lime-rich sediment and fossils, layered over millions of years, was too buoyant to be dragged into the deep. It was scraped away, stripped from the descending slab like mud before a snowplow. This was the birth of the Himalayan wedge. Sediments that once settled in silence upon the tropical seafloor were caught in a colossal vise, compressed, buckled, and driven skyward. Every layer of stone was deformed and uplifted, stacking upon itself to create a mountain range where there was only water. But this was not a tidy, mechanical fold. The massive collision created a chaotic mix of deep ocean rocks and continental shelf, jumbled and forced into a precarious vertical orientation. As we look at these peaks today, the most intimate record of this violence remains physically lodged within the stone. If you know how to look at the summit, you find the evidence of a lost world staring back. A coiled ammonite, caught in the gray limestone of a sheer cliff face, serves as a clock frozen at the moment of extinction. These delicate shells, alongside the branching architecture of corals and the segmented stems of crinoids, were once denizens of a sun-drenched seafloor. They thrived in the stable, warm shallows of the Tethys, shielded by miles of water from the tectonic fate awaiting their home. Now, these same organisms are exposed at 29,000 feet. They act as the ocean's own forensic signature, mapping its final struggle against annihilation. Each fossil confirms that the peak under your feet is the crushed, uplifted, and dehydrated ruin of a marine habitat, torn from its foundation and hoisted into the thin, frozen air. There is a deeper vertigo hidden in that rock. The band of stone capping the summit, the Komolangma Formation, is Ordovician limestone, laid down on a shallow seafloor some 450 million years ago, hundreds of millions of years before India and Eurasia ever collided. The very oldest thing on the mountain sits at its highest point, an ancient seabed carried skyward on the back of a far younger catastrophe. Yet, their presence at such impossible altitudes is remarkable. If the seabed was merely buckled by the force of two continents meeting, it should have shattered into a chaotic scramble of debris. Instead, we see a rhythmic, repeating geometry that implies a systematic process of construction. How did the Earth find the strength to lift these heavy marine slabs by miles, while keeping the structural integrity of the stone so remarkably intact? The answer lies in the sheer volume of material being crammed into a single space. Beneath the Himalayas and the Tibetan Plateau, the crust is nearly 75 kilometers thick, doubling the depth of a normal continent. This is not simple folding, nor the work of a single sudden impact. It is a wholesale crustal thickening, where the rigid Indian plate drives relentlessly beneath the base of Eurasia, stacking layers of stone like a deck of cards. forced into an undersized box. Because the continental crust is too buoyant to be pulled down into the mantle, the collision creates a mechanical bottleneck. The rock has nowhere to go but up. As the Indian plate underthrusts, it drags the northern margin of the continent downward, while the top of the crust buckles and ruptures under the compression of two land masses, failing to slide past one another. The result is a vertical monolith, a massive thickening of the lithosphere that forces the surface to rise in search of equilibrium. Yet, as the geological tension mounts, we have to ask whether this stacking alone provides enough energy to sustain such extreme elevation, or whether a more volatile, hidden engine is driving the range upward from even deeper within the planet. The secret to such immense height lies far beneath the surface, where the rigid Indian lithosphere dives deep into the mantle. This slab does not merely stop at the crust. It acts as a massive, buoyant wedge, lifting the entire Tibetan plateau like a hydraulic jack. Yet even this is not enough to explain the sheer scale of the uplift. Evidence suggests a violent process of delamination, where dense, cold material on the underside of the continental plate peels away and sinks into the hotter mantle below. With this heavy root removed, the crust above is effectively relieved of its weight. Stripped of its anchor, the land experiences a rapid isostatic rebound. A surge of buoyancy that forces the range to climb higher than gravity should allow. It is a tectonic shedding of dead weight, a hidden release of potential energy that turned a plateau into a sky-high wall. This sudden shift in the lithospheric balance didn't just alter the rock, it began to disrupt the flow of the atmosphere itself. As the planet drifted into the cooler, harsher conditions of the Oligocene, Antarctica was locking itself behind a curtain of ice, and the global thermostat was turning sharply toward the cold. Across the Eurasian interior, the once humid forests withered, thinning into expansive open woodland and hardier scrub. This climate pivot was abrupt, ending a verdant era that had stretched toward the poles. As the crust beneath Tibet climbed beyond 3.5 kilometers, the mountains were not merely watching the planet freeze. They had begun to physically reroute the atmosphere, standing as a barrier to the great wind currents and starving continental interiors of the moisture they once relied on. The timing was precise, and it planted a question researchers still wrestle with. Was this cooling a coincidence, or was the rise of the Himalayas itself the mechanism driving the world toward a deeper chill? Either way, this was not just a change in temperature, but a total reorganization of life. The stable, hothouse greenery of the past was being edited down, replaced by a seasonal, drying world where only the giants could survive. Massive creatures wandering an altered landscape, unknowingly living in the shadow of a range that was still climbing. What happened to those giants when the trees they relied on began to vanish? In these thinning forests, the scale of life met an impossible ceiling. Consider the Indricothere, a hornless rhinoceros relative and the largest land mammal ever to walk the earth. Standing roughly 5 meters tall at the shoulder, this browsing titan used a neck long enough to strip the high canopy that still blanketed the region. Its biology was a massive engine designed for constant, high-calorie intake, built for an environment flush with moisture, but teetering on a radical shift. These giants tracked a vanishing rhythm, their enormous frames unable to adapt as the encroaching dry season turned their lush world into a graveyard of dust. The Indricothere occupied a niche that was narrowing in real time, its existence tethered to vast, reliable harvests of greenery that the mountains would soon starve of rain. It was among the last witnesses to a verdant Central Asia before the regional climate reconfigured itself. But the disappearance of such a creature was only the first tremor of a much deeper planetary rearrangement. One that depended on how the elevation of a single, still rising landmass could seize the moisture from the sky and rewrite the life support systems of an entire continent. As the Tibetan Plateau bulks upward past that 3.5-kilometer threshold, it stops being merely a geographic feature and becomes a massive seasonal heat engine. During the summer, this high, broad expanse absorbs intense solar radiation, heating the air columns above it far more efficiently than the atmosphere at lower elevations. This thermal differential creates a powerful, high-altitude, low-pressure cell that acts like a planetary-scale vacuum, pulling the moisture-laden winds of the Indian Ocean deep into the heart of the continent, forcing the air to rise, cool, and dump its payload of water in a relentless seasonal deluge. This is not just weather. It is a systematic rerouting of the planet's atmospheric circulation, tuned by altitude. Yet as this mechanism matures, it carves the continent in two. What happens to the vast interior of Asia once the wall of the Himalayas steals the moisture meant for the far side of the peaks? The moisture is intercepted, trapped against the southern ramparts, leaving the interior to endure a radical, desiccating shift. Acting as an orographic wall, the range forces the clouds to empty before they can reach the continent's heart. This is not a merely regional drying, it is the reorganization of an entire hemisphere's hydrology. Behind the peaks, the once humid forests fracture and give way to the relentless expansion of scrubland and arid steppe. And as the plateau continued to bulk past 4 kilometers, its influence reached even higher into the sky, beginning to fracture the atmospheric currents themselves, bending the jet stream and establishing a permanent trap of cold air over the center of Asia. The world was no longer simply shifting its climate. It was beginning to oscillate. Yet even as the mountains asserted their dominance over the global weather machine, a devastating, invisible conflict was unfolding on their very slopes, one threatening to tear them down as fast as the tectonic pressure could build them. The mountain wall is a battlefield. Gravity, wind, and the relentless biting of glacial ice wage a continuous war against the raw tectonic uplift, forcing the rock skyward. Every meter the range gains is met by an equal measure of destruction. This is not a static monument, but a violent, hyperactive system in a constant state of decay. The monsoon acts as a colossal chisel, stripping away tons of sediment every second and carrying it into the lowlands, while frozen rivers carve deep canyons into the heart of the mass. This rapid erosion is the only thing keeping the summits from climbing toward the stratosphere unchecked. Research suggests that for every centimeter of vertical thrust generated by the Indian plate, the elements scrub away nearly the same amount of stone. A precarious, forced equilibrium. If the tectonic engine ever slowed, the mountains would vanish beneath the weight of their own weather within a geological blink. Yet as this struggle reached a fever pitch in the high peaks, the surrounding world was locking into a new pattern. and the warm, ancient ocean that had defined this region for 100 million years finally began its last retreat. The last vestiges of the Tethys seaways pinched shut, forced out by the tightening grip of the continent. Where once there was an open, sprawling ocean, the Indian Ocean matured into its modern, familiar shape, isolating the landmass as it continued its relentless push. In these shifting, cooling waters, life pivoted to fill the void left by the vanishing tropics. By the Miocene, marine mammals had seized the new order. Whales, already fully aquatic hunters since the Eocene, had diversified into forms suited to the reshaped contours of the globe. Alongside them, early pinnipeds, the ancestors of our modern seals and sea lions, arrived to claim the coasts. The biology of the planet was being rewritten at the same pace as its geography, but this restructuring was not confined to the tides. Deep inland, the rising wall of rock was changing the very composition of the air, because, as the mountain stone shattered under the stress of the ongoing collision, it exposed a vast, raw surface to the elements. A chemical sponge hungry for the atmosphere itself. This chemical hunger triggered a planetary cooling sequence that would define the last 2.5 million years. As monsoon rains and glacial melt ground the high peaks into silt, they laid bare fresh, silicate-rich minerals. These minerals reacted with carbon dioxide dissolved in rainwater, stripping the gas from the atmosphere and locking it away as limestone on the ocean floor. By accelerating this weathering across an entire mountain belt, the Himalayas began to act as a terrestrial thermostat, quietly bleeding carbon out of the sky and turning the greenhouse warmth of earlier epochs into a distant memory. This slow drawdown of CO2 is considered a primary architect of the cyclical ice ages that shaped our current world. The mountains did not simply rise into a climate that was already cooling. They actively chilled the globe toward glaciation, altering the chemistry of the air itself. Remember this thermostat. Nearly everything that follows, the loops we opened at the very beginning, resolves through it. So we return at last to the ghost at the summit. The limestone peaks cutting the sky are the desiccated, pulverized skeletons of the Tethys seabed. And the answer to how an ocean vanishes is brutally simple. It didn't recede and it didn't drain. It was squeezed out of existence, crushed shut between two colliding continents, its floor stripped from its foundation and stacked into a vertical architecture 5 miles high. Every ammonite lodged near the roof of the world is a casualty of that total closure. A marine creature entombed in the very rock that buried its ocean. The sea was not lost. It was rebuilt, standing up into the tallest mountains on Earth. And the pressure that performed this impossible feat never dissipated. It remains trapped inside the rock, held in a state of precarious tectonic suspension because the collision has never actually stopped. India is still driving north at roughly 5 centimeters a year, and every tremor recorded along the main boundary thrust is the sound of that slow-motion impact grinding forward. The plate stalling, slipping, and forcing rock up by another fraction of an inch, even as the glaciers shear it away. When the Earth ruptures here, it is because the internal pressure of the Indian subcontinent has finally overcome the stubborn resistance of the Eurasian plate. These are not the settling movements of a dormant range. They are the stress fractures of a living event. And the same restless motion that lifts the peaks has, for 50 million years, been carving the environments that shaped the life living in their shadow. That ecological upheaval functioned as an unforgiving gauntlet for terrestrial life. As the rising mountains blocked the moisture and fragmented the once continuous forest, large-bodied specialists like the Indricotheres found their vast feeding grounds broken into isolated pockets, and their lineage faded from the record. In their place, a brutal new logic took hold. Species that could cross rocky, seasonal, or arid terrain gained a sudden and massive advantage. This is the deeper reason a mountain range is considered a turning point for all life. Not because it killed, but because it selected. The same drying, fluctuating pressures eventually reached the ancestors of the hominins, who were forced to evolve in a mosaic of open woodland and expanding steppe rather than a stable, endless canopy. That shifting world demanded new mobility, new social cooperation, new ingenuity in finding food. It is no accident that our own lineage emerged as the climate swung between glacial cold and the dry, sharp seasons the Himalayan wall helped catalyze. By rewriting an entire continent's environment, this single collision became a primary architect of modern mammalian diversity. And of us, we are the inheritors of an evolutionary trajectory steered by the very uplift that tore the Tethys floor from the sea. The world it left behind bears almost no resemblance to the one it replaced. The Eocene had been a seamless greenhouse, angiosperm forests running unbroken across the continents. The collision shattered that continuity for good. What was lost was not a single species, but an entire mode of life. The warm, uniform, deeply interconnected biosphere of the early Cenozoic, edited down into a volatile, temperature-driven patchwork of habitats, divided by rain shadows and seasons. The lush corridors that had let giant browsers roam a whole continent were severed into shrinking islands of green. This was the true cost of the mountains, a planet that traded richness and stability for variety and volatility. A biosphere forced to fracture into the mosaic we still live within today. And that fracturing forces the oldest question of this story back to the surface. Was the great Oligocene cooling that began it all a mere coincidence of orbit and chance, or the physical fingerprint of the rising rock? It was no coincidence. The evidence now points in one direction. As the Tibetan Plateau clawed past the 3-kilometer mark, it forced the high-altitude winds to split and shudder, reconfiguring how moisture moved across the entire planet and locking continental interiors into cycles of seasonal drought. And as we have seen, the shattering of that same rock exposed the silicate surfaces that pulled carbon dioxide out of the air. Two mechanisms, one mountain range. The winds reorganized the weather. The weathering reorganized the atmosphere itself. The deep chill of the Oligocene was not an accident of orbital mechanics, but a direct consequence of the geological machine India and Eurasia had set in motion. The mountains did not just witness the cooling of the world, they caused it. And in doing so, they set the stage for a seasonal pulse of moisture so violent and precise that it would come to command the fate of an entire civilization. For billions of people across South and Southeast Asia, that pulse is the difference between life and famine. The monsoon the plateau ignites controls the annual filling of the aquifers, the timing of every planting, and the yield of the region's staple crops. When the circulation is strong, the harvests are bountiful. When it stalls, the shortfall is felt from the fields of the Ganges to the crowded cities of the coast. This is the astonishing reach of a 50-million-year-old collision. The height of a plateau raised before the first primate walked upright now acts as a primary filter for human food security. The rains that will fall this summer, feeding more people than any other weather system on the planet, are timed by a wall of rock built from a drowned ocean floor. The deep past is not behind us. It is in the very moisture falling from the sky. Yet for all their reach, these peaks are not the fixed, eternal monuments they appear to be. Measured against the age of the Earth, the Himalayas are startlingly transient. We exist in a momentary window, catching this crustal architecture while it is still actively rising. And our entire history, every civilization and written record and turn of the human mind, has unfolded in little more than a heartbeat of the range's 50-million-year life. To grasp that is to feel the ground shift beneath one's certainty. From the highest jagged pinnacle to the base, how do we come to terms with a monument that is already destined to vanish? We come to terms with it by seeing the whole collision for what it was. A single hidden architect behind nearly everything about the modern world. One crash closed an ocean and raised the tallest peaks. It switched on the monsoon that waters half of Asia. It cooled the entire planet toward the ice ages. It fractured the forests and steered the evolution of mammals and of us. The predictable swing of the seasons, the very stability we build our lives upon, is the byproduct of one unrelenting, ongoing impact. The history of life on the surface of this world was quietly written by the grinding of rock and the rerouting of wind, far beneath our notice. But there is a cold, final friction to this system. The engine that raised the range is finite, and its momentum is already beginning to wane. Even now, the slab of Indian lithosphere deep beneath Tibet is changing. Geologists have identified regions where the cold, dense leading edge, the driver of the entire Himalayan engine, appears to be detaching from the crust above and sinking into the mantle in a slow-motion rupture. Without that continuous pull from below, the range will eventually lose its anchor. The forces now locked in their delicate, violent standoff, uplift against the endless gnawing of monsoon and ice, will tip out of balance. Once the deep engine falters, the mountains will no longer be fed by the internal pressure that holds them aloft, leaving them exposed to the one force that has never rested: gravity. And as the range begins to lose its grip on the sky, a final, slow-motion decay will reshape the continent all over again. As the northward push finally stalls, the crust, no longer squeezed into a thickening wedge, will begin to thin and stretch, shedding the mass that held the Himalayas up for tens of millions of years. Rivers that now carve deep, sediment-choked canyons will keep working as natural scalpels, shaving the summits down grain by grain. Glaciers will expose the raw, crumbling internal structure of the range to the weather. What is today a sky-piercing wall will be lowered into broad, rounded hills, and finally into a low plain, and the very fossils now locked in the peaks will be washed into distant river deltas and recycled into the cycle of sediment that first birthed them. In the Tethys, we are witness to a transient triumph of rock over gravity, and the clock on it is already ticking. Standing here today, we are perched on a razor-thin moment of balance, a fleeting pinnacle in a story already moving toward its end. We have arrived just in time to see the mountains at their tallest, witnessing a peak that will exist for no other observer in history. And once you learn to read a skyline this way, you see the same story everywhere. Every mountain range on Earth is a tombstone for a sea that no longer exists. The Alps are the crumpled wreckage of a branch of the Tethys, squeezed as the African plate ground north into Europe. The jagged spine of the Andes is not merely volcanic fire, but the result of the Nazca Plate diving beneath South America, buckling the continental edge into a long scar of peak and plateau. The weathered, rolling Appalachians look gentle now, but around 300 million years ago, forged in the collision that assembled Pangaea, they stood as tall as any range alive today, before deep time chewed them down to their crystalline roots. Beneath the soil of every continent lies the folded, fused remains of worlds that were crushed and discarded by the same shifting tectonics. A skyline is never just a backdrop. It is a ledger of what the planet has collided with and what it has managed to destroy. This is the secret truth buried in the map. The Himalayas are not an isolated accident, but a single entry in a vast global ledger of crustal violence, and we happen to live in the quiet lull between impacts. Even now, the collision does not sleep. Beneath the Mediterranean, the crust is already buckling as Africa presses toward Europe, preparing to swallow that sea and raise a new range in the image of the ones that came before. Look closely at the hills near your home, and you are likely seeing the ruins of an older, vanished collision that long ago lost its battle with gravity. We are guests on a world that is constantly being broken and rebuilt. A planet that does not know how to sit still. Every landscape is a record of these deep time cycles, the assembly, the climb, and the inevitable decay. We simply happen to be here in this one violent chapter to witness the peaks before they fall.